Alright, so today we're doing the famous direct comparison test. This one I think is going to be kind of easy to explain. Let's give it a shot. So imagine that you've got some sort of sum here that's not so pleasant to look at, maybe a little bit tricky, and you think, well, who knows? But if you can relate it to something that is much easier, and if luck is on your side, maybe we can do something about it. Let me try to make a picture of what's happening here and the thinking involved. If I was to make a picture of this graph, it'd be a little crazy. I know it goes down because the denominator, as it grows, the quotient gets smaller. So I know that the graph would go something like this. It would go something like this. And we're going to call this graph 1 over x to the third plus the square root of x. By the way, we can, because it's decreasing monotone and all that, we can use the integral test. So basically this problem amounts to the same as that problem. They will both converge or diverge. But I noticed that there's something a little tiny bigger that I can easily handle. Namely, if I made the denominator just the n to the third, just this piece alone, forget about that piece, that I could easily do because the integral would be much, much simpler. I could do that in a couple lines. And I'm wondering, how does that compare on the picture? Well, I think that it's a little bigger, and so it would look something like this. It would just be just a tiny bit to the right, or sorry, to the top, and it would go something like this, and this one would be 1 over x to the third. Now here's the deal. If I was to integrate 1 over x to the third as x runs from 1 to infinity, this would give me x to the negative 3. That would be negative 2 over 2, going from infinity to 1. That would give me 1 over 2 times infinity squared minus 1 over... actually, it should be negative. 1 over 2 times 1. So that would give me actually 1 over 0, negative 1 over 0 plus 1 over 2. So that would be equal to finite. So I know that if I was to calculate this area right here, it's finite. That is finite. The one under the orange curve, the simpler curve. This one over here is even smaller, and it doesn't go all the way to negative infinity. It stays positive. So this one is squeezed between 0 and something that's finite. The area under the yellow one, which is this one, has to be finite because it amounts to less than this entire area, which we already showed is finite. Something smaller than finite has to be finite. Well, as long as we keep them all positive. Does that make sense? So that's the essence of the comparison test. Maybe AN is way too difficult to figure out. AN is way too difficult. But if we knew something that is much easier, and we know it's finite, so B is easier, well, it works both ways. If you can show that this guy is smaller than something that you know is finite, then this one will be finite. Or if this is your difficult one and you know it's bigger than something that is infinite and this is even bigger, well, then that would be infinite. And so it works both ways. You can prove that you can use it to prove something is infinite, or you can prove it to use something that's finite. In this case, we're going to be showing that it's finite. So here we go. This is your these are your ANs, and of course here's how I can prove that this, what I was saying is that the red one is actually larger than the area under the yellow one. We can go something like this: n to the third plus square root of n. That's definitely bigger than or equal to n to the third. That's because you're adding more stuff to it. You're adding square root of n to each one of these terms, so of course it's going to get bigger than just the n to the third. Flip that and you get 1 over n to the third plus square root of n is smaller than or equal to 1 over n to the third. And because all these n's are starting with 1 and going all the way to infinity, everything is positive here. And so then the sum, slapping a sum on this side as n runs from 1 to infinity, slapping a sum on this side as n runs from 1 to infinity, There's no need to slap a sum on this side because that's just going to give you 0. And we already showed that this is finite. So now we have some number here that's larger than 0 and smaller than or equal than something to something that's finite. That forces this one to be finite. And you can conclude, therefore, that the sum of all the 1 over n to the thirds plus the square root of n, as n runs from 1 to infinity, converges. Okay? That's the gist of it. Squeeze it between 0 and something that you know is finite. Same thing here. This guy is definitely smaller than or equal to summation of all the n squares as n goes from 1 to infinity. This is finite. All these things are bigger than 0. Therefore, we have convergence by direct comparison test. Okay. This one, same thing. I have that 1 plus sine of n. That would always be less than or equal to 2. And that would always be less than or equal to... this would be greater than or equal to 0. So then dividing by n squared plus 5, divided by n squared plus 5, gives you that. Then you stick a sum on every side. And so you get that... actually, this one you can even make it even more easy. You can say this is less than or equal to the summation of 2 over n squared. By making the denominator smaller, I took 5 away from it, I make the quotient bigger. So then we have that 0 is less than or equal to summation of 1 plus sine of n all over n squared plus 5 as n runs from 1 to infinity, and that's less than or equal to 2 times the summation of 1 over n squared as n runs from 1 to infinity. And that, of course, is finite. It converges. Finite. In fact, I know what it converges to. It's the basal problem. Might as well just say it here. It's super famous. This is pi squared over 6. As proven by the most amazing mathematician ever, Euler. All right, so now we've got something that is less than finite and bigger than 0. That's it. By direct comparison, then, this one converges. Okay. So all these examples show me convergence. I think I should write an example where I show divergence using the comparison test. Suppose I wanted to find the limit of 1 over n plus ln of n. We're going to change this to n minus ln of n. How would you show this is converges or diverges as n runs from 1 to infinity? I could put a 1 there because if that was a 1, this would be 0, this would be a 1, so the denominator would be okay, it wouldn't be 0. That's why you paused. But anyways, here's what I'm thinking. N, I'm going to think yellow. N minus ln of n, that has to be bigger than just n. Right? Sorry, just testing you guys, see if you're paying attention. That has to be smaller because you took something away from it. Or you could do it the other way around. You could start off with n is less than, n is for sure, n plus ln of n is definitely greater than just n, so therefore n is greater than n minus ln of n. You could do it that way too. Okay, now what would happen when I flip these? 1 over n minus ln of n, that would be bigger than 1 over n. When you flip these, you got to flip the sign of the inequality. Then I'm going to slap some sums on here. The summation as n runs from 1 to infinity, as n runs from 1 to infinity. Now this one, we've done it before. We know it's famous. It's a harmonic series, and we know it diverges. So this is equal to infinity, right? And now we've got this guy that's bigger than infinity. So now that leads to the inevitable conclusion that the summation of 1 over n minus ln of n is bigger than infinity, as n runs from 1 to infinity. Which numbers are there that are bigger than infinity? Well, I can only think of one off the top of my head. It's infinity. So 1 over n minus ln of n is diverges. It diverges. See, so in this case, we took something that was a bit complicated, but we noticed it was bigger than something that was much, much simpler. And we noticed that that thing was already equal to infinity. Since this one is bigger, it forces that one to be infinite and diverges. This is called the direct comparison test. And this was going the other way around. The other previous examples I did were proving something is finite. This one is proving something is infinite. You have to change the sign of the inequality depending on which way you're going. All right, I think that'll do it for now. This is a real simple introduction to direct comparison test.